We have a full program in June from the 9th today through the 16th, 23rd and 30th. I'll introduce Andy in a moment or two, but before getting to that, on the 16th of June at the same time, 2 o'clock, you'll see a panel discussion on offshore wind featuring Ben Sykes from Ørsted and Tony Quinn from the Catapult. Janie, one of our key researchers, will be in the chair on the 23rd, and she will talk to hydrogen and its use in transport systems. And at the end of the month, we'll be looking at the just transition with Simon Abram on the 30th of June. So you will get a reminder for those, of course, from Lynn, but do put them in your diaries and make the most of this series. On for today, and it's delighted to invite Dr. Andrew Smallbone to give a talk on decarbonising heat. Just for a little bit of background, some 70-odd% of heat in the UK is still supplied by burning fossil fuels. And given that half the energy bill in the UK is around space heating and water heating, this is still a massive challenge, which has received, up until the last few years, very little attention. There's a great deal of work going on in the Energy Institute on decarbonisation of heat, tongue-tied there, and Andy leads a lot of that. So, Andy, would you care to tell us more, please?
Thank you very much, John. And I think I would say thank you for inviting me to give this what initially was going to be a brief talk, but now a much longer talk on decarbonisation of heat. I should say that most of the activities that I'll be talking about are related to research by myself or my colleagues in Durham Engineering or Durham Energy Institute, but also there's a splattering here, particularly on the introduction, which from my lecture notes, which I give a course on the decarbonisation of heating and cooling, which is going to be part of the new MSc program, which will be launching in the September time. So if you're interested in these topics, there's a direct course that you could get involved with there. So to come back to the topic, the decarbonisation of heat. So what I'll try and talk about today, when my computer allows me to turn over the slide, which is not actually working here. Maybe I'll try this one. Okay, there we go. So so briefly, I will talk about the challenge of heat in a net zero world. I'm going to talk about the opportunity that exists for hydrogen in context with other potential ways of hitting net zero for heating. And then I'll talk about a specific case study that we've been looking at as part of the team on a local hydrogen-enabled energy system, and then I'll summarize that. And then if there's time, I'll talk about some of the opportunities that we've got through the Net Zero Research Network, which is another activity that we lead on the decarbonisation of heating and cooling. So the challenge of heat is quite important, I think, when you look at it in the context of this very simple pie chart. And I'm sure, like me, everyone enjoys pies. And this itself represents, you can see what the final energy demand is across lots of different sectors. And this really comes from the final energy consumption from the OECD countries. So this is typically the wealthiest countries in the world, and has been collated by the International Energy Agency. And this shows you what, as consumers of energy, we actually expend our energy on. And it usually surprises people to see that heat is actually about a third of the energy use, transport a further third, and then everything else in the final slice of the pie there. I think you can kind of close your eyes when you talk about and think about energy policy, and you see the pictures you see in the media around energy policy. And principally, they only show pictures of transport problems and electricity problems, but actually the forgotten cousin has been heat over the years. And I think that's now going to have to change quite dramatically. When you look at that heat segment there, you can see where heat is actually used and who it's used by. And we often focus really around and think about heat as a problem for heating our own homes, because we kind of see it on a day-to-day basis, but actually residential heating is only a third of that actual space. Commercial buildings, a minor user, and obviously agriculture, but the main end user is actually industry, and that's heat for industrial processes or dealing with large volumes of or trying to process the production of different commodities and so on. So it dwarfs the amount of energy that we use at residential scale. So the decarbonisation of heat is a decarbonisation of ourselves and industry and all of our industrial processes. And many of the things that I'll be talking about and explaining will cut across, hopefully, all of these topics. And then to take that idea further and then come back to the original pie chart and look at some of the challenges here around transport. If you look at transport and you think about transport in itself, most vehicles are actually 25% efficient and are carrying and using petroleum as their driver and powering the system with that petroleum. But actually, with a 25% efficiency, the rest of it is lost as heat. So that 32% is actually, most of it is heat itself or lost as heat. And you could say similar things about electricity as well. For example, this data set includes energy users from the Middle East, and up to 50% of their peak electricity use is actually used for cooling their buildings and properties. So again, it's starting to fill up the pie, actually, that in practice, heat is a major challenge. And then you have to remember also that electrical systems, in practice, a lot of the inefficiency is because they get hot, and you're trying to get rid of the energy from that out of the electrical system. So you can start to see that actually we start to build this pie up quite considerably. Some of this, some of these could be discussed and debated, but ultimately it leads to the picture that actually the decarbonisation of heating and cooling is very complex, and it cuts across almost every problem in decarbonisation. And many consider it to be the most challenging element of reaching a net zero. So you've got this overarching challenge, and then you've got the thing that makes it rather different to transport and electricity, because heating is different because there's a direct link to mortality. So any, turning off and not driving a car, this is possible, but turning off your heat is not possible because obviously there's lots of negative impacts on that. And when you start to look at what's happened to society, and this data here comes from London, when the temperature goes down, you start to see why. So this is data from London. Across the bottom there, you can see what the temperature was when somebody died. A very morbid picture, but you can see that the majority of people die in moderate temperatures. But the line you can see there at the top, this one shaped as a U shape, this is actually the relative rate of death as we move to the extremes of temperature. And as the outdoor temperatures drop below 2 degrees here, you can see that we get a very rapid rate of the increase of people dying as a result of maybe not directly because of the heat, but you see that actually the death rate increases. Now, if you contrast that with other places, this data here is from Stockholm in Sweden, and maybe their infrastructure in Sweden is more appropriate for lower temperatures, and you can see through the addition of things like technology and different ways of dealing with cold, that they actually have managed to solve this problem. They no longer have a tick which goes up. So you can do things to actually alleviate the problem of increased morbidity as a result of reducing temperatures. Now, technologically, there's lots of different solutions that are out there for hitting net zero with and delivering on net zero targets whilst keeping the heating on. and many of them are kind of mapped out in this slide here. The most common and the one really people have talked about considerably to date has been around improving efficiency and dealing and increasing the amount of insulation in your properties. This has been a driver and has been something that's been going on well before we started announcing net zero, as has the implementation and increasing use of heating and cooling networks. And these two things will go on in parallel with our race to net zero, I'm sure. This heating and cooling network has been constantly there through many generations. It's never really happened for practical reasons, and we may not well see this done at scale before the 2050 targets. We certainly need residential heating and cooling solutions. In the UK, we obviously have well-established platforms for delivering residential heating, but we're also expecting to see temperatures rise in the UK, particularly in the inner city. So we may well see quite considerable changes in the amount of times you see air conditioning installed on the side of a property. Heat from hydrogen is a key topic that we engage with quite heavily at Durham, and a lot of this talk is dedicated to talking about it. As is heating and cooling from renewable electricity, and of course renewable electricity, has its own intermittencies, and therefore we need to deal with that somehow, and complementing that in a way which works with heat is a very interesting and very important topic. Industrial heating and cooling solutions are very bespoke. They're not necessarily dealing with the same kinds of temperatures you would in a residential scenario. They could be, and they range in hugely from very high temperature down to low temperature. So many of these will need to be decarbonised directly or indirectly through different means. As is often forgotten, we do rather a lot of drying in the UK for different reasons, and there needs to be solutions which are compatible with net zero for that. And it all needs to fit in with an integrated energy system. And what we mean by an integrated energy system is some kind of complementarity. So this is a race to decarbonise the UK, not just transport, not just electricity. It does need to include heat. And there's a lots of synergies between these different sectors which could benefit one another. It may be as simple as selecting certain approaches and certain primary energy sources to do heating. It may be more integrated than that, but ultimately we need to be thinking together about how these things are done. This talk focuses on heat from hydrogen, heating and cooling from renewable electricity. There's some links with industrial heating and cooling, and we're certainly going to be talking about integrated energy systems. Now, there is a huge opportunity for hydrogen, and this is what we've been spending a lot of time and energy on in the last couple of years. The world is changing very fast, and this is the trajectory of things changing in and around renewable energy. What this chart here shows is the relative change in installed capacity and the installed cost of different kinds of renewable energy technologies. On the first side here, which is the historical kind of orangey color, this is based on historical data. And some of these plots show the relative cost of onshore wind, electrolysis, offshore wind, lithium-ion battery technology, and PV technology over the last 10 years. I think some of them actually start plotting up there, but you can see over the last 10 years, these have all come down to the datum and the middle point here, which is the 2019 date. There's data. This is all based on International Energy Agency data. So they've all come down, and they've all followed this kind of trajectories where the more you install, so this is what this axis here, the more you install, the more the cost of that system comes down. The gradient is often to do with the technology itself, but it's an interesting observation that's happened. It's happened in other sectors. It's happened in consumer electronics and energy in general, that these trends tend to follow what's called a learning rate. And you can fit these different learning rates. And in terms of being someone who carries out research in these technologies, it's quite demoralizing to think all of your activity just follows a constant line. But it seems to be the case that this is the way these things tend to move. If you then start to project these forward and you take them into the where these things are expected to go within the 2030 and 2050 lifetimes based on different kinds of analysis that people have done, you can see actually how much these things are going to change over the next 30 years. And this line here represents a scale up of 10 times greater than what we currently have installed. And this is over 100 times scaled up what we have. And you can see that in the 2050s, we're looking at many times, tens of times more installed capacity of most of this technology. There are some estimates which take many of these even over into the hundreds of times, many hundreds of times scale up. But kind of historically, this is an unprecedented rate of installing equipment and changing a society. So it's really interesting and really fascinating to see. The big question is, can these lines continue? Because essentially, lots of the investment decisions that are going around are assuming that they all do continue to go down at different rates. The kind of winning technologies, the ones that are going to dominate, may currently deviate from some of these lines, and it may well adjust lots of the different assumptions that people are making around what will the future look like in terms of energy. So coming back to the hydrogen question, so this is an image here that I've created to sort of map out one of the pathways that lead to hydrogen. There are obviously different ways of producing hydrogen. There's bio-related ones which are interest, but the ones at scale, I guess, the principal ones that can reach the kinds of scale that we need there for the hundreds and hundreds of times scaled up that we need, relate to the conversion of natural gas to hydrogen and storing the carbon dioxide underground, but also one that's considered more longer term potential is green hydrogen. And that's what's shown here. So that's the usage of renewable energy shown here with the red dot being electrolyzed. So that's converting water plus electricity into hydrogen directly. And that hydrogen itself can be stored in a gas storage system and then returned back into a form which could then be deployed directly to produce electricity, which could then support the grid for when the renewables are not being used. Of course, that same grid could also feed electricity into the electrolyzer, but it wouldn't necessarily then count as green, but the infrastructure would be there to maintain a constant supply of electricity if required. Furthermore, the same system brings resilience and more flexibility through doing so, because the hydrogen could then, if there was an abundance of it, be supplied to the gas network potentially and distributed locally. It could be distributed to industry as a direct feedstock for many industrial processes. It could also be used within industry to provide heat for their local infrastructure. Obviously, hydrogen's got the potential for use at large scale within transport, particularly at the heavy duty end of the scale, long distance travel, where battery electrification has got its own limits. It can be used for heating and power in buildings. So there's a huge number of potential end user applications for the technology. And this will be driven principally by the cost reductions that come from electrolysis and the additional cost savings made by reducing renewable costs. Many consider this pathway here to be cheaper, the cheapest way to produce hydrogen from the mid-2030s onwards. So whilst the short term, we may well see the use of CCS as a model to remove the carbon from natural gas, its long-term application is through electrolysis here. And what we've been working with in Durham is to build up a heat laboratory for hydrogen for heat laboratory in our Belmont site. And this has been done through a grant from the Northeast LEP, where we've kind of built a platform which will allow us to demonstrate this kind of an energy system in practice. So the first thing we've got is we've built an electrolyzer system and gas storage system where we can then demonstrate the pathway of renewable into the electrolyzer to store hydrogen and then deploy that as electricity and provide that back to the grid. And we're starting to finish this system and start to commission it right now. We've also starting to commission a combined heat and power system, which will obviously be able to produce electricity from hydrogen, but also be able to produce heat for buildings. And also the same system could also operate on a transport vehicle to provide electricity on board the vehicle. We're involved in the IDRIC project, which is the UK Industrial Decarbonisation Research and Innovation Centre, which is a £20 million investment into academia to support the decarbonisation of industry. And we're going to be working closely with the Teesside cluster on their transition to net zero. And we're going to be modelling the industrial network and energy networks locally and embedding hydrogen in there to see how it could be best supported. Finally, we're involved in the Future Grid project run by the National Grid, and it's called Future Grid. And the objective is to supply 100% hydrogen into the national transmission system and to understand its dynamics. So that then enables us across our laboratory to analyze all the different nodes across this potential future hydrogen energy system. Now, coming back specifically to this chart, which I was mapping out and talking about earlier, I was focusing on this blue line now, the line that has been plotted for electrolysis. And if we focus in that on more detail and we plot only data for electrolysis in there, we kind of come up with this more detailed graph. So up here at the top, you can see some of the raw data that's available for large-scale electrolysis in terms of its costs. Okay, the data up here is from around 2010, and as you can see, there's not that much data back in that period of time, and there's more data as we move forward. That's simply because the availability of large-scale deployment of PEM electrolysis is only a relatively recent activity. So there's very little data to base this on. And again, that's historical measurements. If you then start to look at this data in more detail and think, well, this is how a power law can be fitted through this data to kind of make an estimate as to what the future costs might be, you can start to see that actually you could probably fit this line through this data set a number of different ways. A lot of the weightage is actually towards this one here, for example. So by playing with those kind of parameters, you can actually start to see how important, and this blue area here represents all the different ways that you could potentially selectively draw lines through this data to kind of show the uncertainty that there really is around the cost of electrolysis going forward. Now, what I've also plotted in here is different analysis and different activities that people have tried to estimate the future price of an electrolyzer system. Some of them are more pessimistic than others, but overall you can see that they're all expecting costs to come down quite significantly. I guess around the 2030 era, we're looking at 10 times what we've got of our current installed capacity, and then maybe 100 times around the 2050 timescale. You can see actually as you move to some of these other analysis, they're expecting renewable hydrogen to scale up more than 200 to 300 times compared to what we've got right now. The key bit is that everybody is stating the future of our energy system on this extrapolation, which is quite an interesting situation to be in. Like we're talking at the moment that there's 30 major nations which have invested in hydrogen. More than 200 large-scale projects have gone out, and people are investing 70 billion into the costs and trying to estimate what's going to be happening here in this future energy system. So society is betting very big on hydrogen, but there's actually quite a bit of uncertainty as to whether or not those costs can be realized. So what we wanted to do was to try and understand this dynamic of what is the future price of hydrogen, and how could this be achieved. So we started to look at this opportunity. So we wanted to do an evidence-based exploration of the cost reductions associated with green hydrogen production. And actually this is some work that's currently under review by the team. And what we did was we went out and we built what's called a techno-economic model. So it brings together the data that we've got around the technical side of a system, and tries to understand also at the same time the economics of building such a system. So we based our analysis around building lots of smaller electrolyzer systems that could be deployed in parallel. So we based it around a 200 kilowatt system. I built a technical model of that system, reflecting the efficiency, energy consumption, and the required different sizes of different components within that system. We then built an economic model, going through component by component, trying to understand each component's cost, its potential supply chain, and then finally bringing forward a model of the manufacturing process itself. Again, manufacturing each component in a common site, understanding what raw materials they required, the production line itself, including the staff, and then to take that from a system which was maybe producing 10 per year to thousands per year. And as you can imagine, this would start off with a small team building by hand, and then at the other end of the scale, we would be producing thousands of units, and it would be either automated or semi-automated. Now, when you look at the model that was developed, we kind of start off with raw materials. We then figure out what are the subcomponents of an electrolyzer system, worked out what the labor costs, the energy costs, the building rent costs, any waste, any capital that would be required to build them, and then to build that up into the components that build and could be used to assemble the system. And then you end up with the full system, the full PEM electrolysis system. You can see here from this chart here, at the bottom here, we've got the annual manufacturing capacity. Note that this is a non-linear scale, it's a log scale. So here we've got a very small number of units being built per year. And at this end, it's the 5,000 units being assembled. And as you can see, as you scale up the size of your plant, the costs, the total cost, which would be the sum of all of these different components, actually comes down. You can see that moving quite dramatically down there from about $2,000 per kilowatt down to about $500 per kilowatt as you move through this curve. You can see that it's broken down quite interestingly. It's broken down by individual components. The stack, which is, I guess, is the main bit, the electrical, the stack of electrodes. That's the blue. The balance of plant, which is basically the supporting infrastructure that cools the system or dries the system. That's the orange here. You've then got installation costs, and then the top bit is the markups. The business who's building these systems has got some kind of profit. And as you can see, when we start building at small scales, the main costs is actually the stack. But by the time you're manufacturing and having a more automated and more a larger scale assembly plant, actually the stack costs become much less significant relative to the overall cost of the system. Yeah, and by that point, the balance of plant costs are actually the dominant cost of the solution. And you can trace that back through all the components and all the subcomponents to see where and what parts of the stack and what parts of the balance of plant are actually driving that. So in the case of the stack, as you move in this direction, you're mainly dominated by the raw material cost of the system and less by the human or resource intensive aspects associated with having staff. So you can see that we're likely through the scale up of the manufacturing of this system to be able to make dramatic savings on the cost of the system. And we can take that idea a little bit further and go from the capital cost of an electrolyzer system to establish a levelized cost of hydrogen. Now, building on the capital cost of the system, you can make lots of different assumptions about what's the future electricity price, how much would you use the electrolyzer, so its capacity, and also the kind of operational cost of a large scale plant. And ultimately, this is what yields your levelized cost of hydrogen. We've made across both of these some simple assumptions, but there are lots of ways of painting this picture, but generally the story is as I describe in the next few slides. Now, for context, often hydrogen is represented in hydrogen per kilogram. This is quite convenient because actually about 1 kilo of hydrogen has got the same amount of energy as 1 litre of gasoline. So for parity in your own eye, when you see that 1 kilo of hydrogen, you can relate that back to a litre of fuel. But what you can see here is that as you move from the large scale, the small scale manufacturing to the large scale manufacturing, actually the cost of electricity is overwhelmingly the most important factor in driving the price of hydrogen. Initially, at small scales, like in the current times, actually it's the capital cost of the system plus the electricity, but actually the system itself becomes much less dramatic as we're manufacturing more and more of these systems. Now we can take that and start to then think about, well, what about if we scale up to 10 times or 100 times of green hydrogen? The levelized cost of hydrogen currently would sit around here, this kind of figure from this kind of technology, and we would estimate that manufacturing cost savings that I just described would reduce this down by about a third, which if we were manufacturing at 5,000 units would give us a cost of 416. And then if we start to scale up 10 times larger, we would start to expect to see other factors coming in. So we would expect to improve the efficiency and the lifetime of our system. And we would also, during that time, expect to see the offshore wind costs coming down. So offshore wind is probably going to take off another $1 off of that price, bringing us down to the $2.63 at the 10 times scale up. Again, we could go forward and take that up to 100 times scale up, and a similar trend would exist, which would take us down to the $1.57. $1.57 for a kilogram of hydrogen would be very disruptive and would be transformational in terms of the sector. But you can see there the story through how the price of hydrogen is expected to come down is shown as a combination of this manufacturing savings, some improvements to the system, as well as savings driven by offshore wind reductions. So this has implications, and these costs have implications on what might happen to the hydrogen economy. The first is to show that same chart again, and to remember again that there are many pathways which lead to hydrogen, and we are focusing on just one. And of course, there is the opportunity for scale here. But the most common question you get is that there are other pathways to obtaining and coming to a decarbonised economy, and these need to be considered in context with what's happening here. So the first thing to say is that we've focused principally on the cost of hydrogen production, but there's other factors as well when it comes to the cost of a system. you've got the distribution of hydrogen. So that could be through pipelines, it could be through truck delivery, or it could be through of gas, or it could be truck delivery of liquefied hydrogen. So there are different ways of moving it around. And also there's a difference between the way every end user might use hydrogen or might use another decarbonised option. So these all need to be considered when thinking about, well, what's the most effective way of decarbonising my system. So it's very difficult as a result to come up with a holistic answer to say what's the best option, because there's so many factors involved, but we'll try and paint that picture in simple terms. So what I show here in this bar chart is what the required hydrogen price is to become the cheapest option on the basis of a total cost of ownership model. For simplicity, we're going to assume that hydrogen gas is distributed via a natural gas network which already exists. So somewhat similar to what we have today, but the hydrogen system has repurposed the natural gas network. This has been selected on the basis that it's the cheapest model for distribution. And if it doesn't work here, then hydrogen is more challenging to deploy in other ways. So that's why this one's been picked. And you can see here that the chart shows four prices of hydrogen. The price in 2020 from renewable hydrogen, one on the basis of the 10 times scale up that we've just calculated with an uncertainty in blue, and then a similar with 100 times scale up shown with the green. And we also show the nominal target, which is what a lot of investors and technologists use, of the $1 per kilogram target for hydrogen. But I show it here as 2 because we've added on the cost of distribution as well. You can see immediately that the cost would come down as a function of scale up. And the first one here, the first comparison here, is to show what the price of hydrogen would need to be in order to replace one particular solution. And that first solution is to replace the heating demand from a building. And that would be an existing building which has been retrofitted with a heat pump, plus doing all of the efficiency retrofitting in and around insulation. So that's taking an existing building, insulating, and then installing a heat pump. So hydrogen would, on the basis of this analysis, show that this is actually very viable to do almost right now. It would be cheaper to do this with renewable hydrogen than it would be to take that installation and take that forward. That's simply because, in terms of the cost of ownership, you're replacing the gas boiler with a hydrogen boiler, which would not have such a huge difference in terms of capital cost, but you wouldn't need to do all of the invasive and expensive insulation activities that would be associated with installing it with an alternative heat pump. So this appears to be a very viable pathway for decarbonising existing infrastructure. When you take the same approach and you look at it in terms of a heat pump installation, but the heat pump is now installed into a new build, and all of those same efficiency measures are installed into the new build at the point of assembly and construction, then the cost, then the required price of hydrogen to beat that becomes much lower. So you would need then, it may not be possible to do that until after a 10 times scale up. It would be more cost effective to install a new build with the heat pump in the short term, certainly, and probably into the longer term as well. So even with 100 times scale up, there would still be this debate whether a heat pump or a hydrogen installation should be carried out. And then we've got the 3 other scenarios here, which really illustrate part of the overall challenge here. So we have the opportunity to use and replace natural gas combustion to generate electricity, or natural gas to produce heat for an industrial process, or to replace natural gas into a gas network in that form. In order to be equivalent price to the natural gas, we would approximately need this nominal target of $1 per kilogram, and that may only be possible at the 100 times scale up in the most extreme scenario. And this illustrates the challenge of cost and illustrates the fact that the price of natural gas is very low, and replacing natural gas is much more difficult than perhaps comparing with other net zero solutions like the heat pump here. So quickly to summarize hydrogen is an option for heat, transport, power and energy storage, and a scale up of green hydrogen is up to 100 to 300 times expected to deliver net zero targets. Green hydrogen is expected to become cheaper than blue within the next 15 years. Mass manufacture, lower electricity costs and improvements are expected to reduce the capex and overall cost of these systems. And then even at the 100 times scale up, a net zero heat is more expensive than fossil derived fuels. And this last point is extremely important. We often think about net zero heat, but obviously, as I described at the very beginning, there's obviously a link to mortality for high, if not enough heat is available at cost. So now I'd quickly talk about a local hydrogen-enabled energy system. And this one is related to a project we're undertaking called Zero Carbon Emission Integrated Cooling, Heating and Power Networks. And effectively, this project looks at the techno-economics of hydrogen-enabled energy systems and attempts to quantify their value in terms of resilience, flexibility, and to demonstrate them in the lab. And we're also quite keen to look at consumer attitudes to hydrogen, which I guess initial feedback from lots of projects that have looked at consumer attitudes may well be overstated in terms of consumers being in fear of them. And what we wanted to look at particularly was around the opportunity of an energy system where a large-scale PEM electrolysis was carried out. What we know is that the electrolysis system is between 60 and 70% efficient. So that's 60 and 70% of the electricity turning into hydrogen itself. The rest is actually lost as heat or dumped as heat. Interesting, the temperatures of that heat are quite high and actually are quite compatible with the kind of temperatures you might want in a heating network. So given that fueling stations are often closely co-located with buildings and commercial buildings, we wanted to look at the potential for a combined heat and hydrogen system, where the heat would supply energy or thermal energy to residences and commercial buildings, and the hydrogen would be used to fuel transport vehicles. So just to kind of illustrate what that would look like, so renewable electricity would be supplied to the PEM electrolyzer. The PEM electrolyzer would then provide hydrogen and store compressed hydrogen for use on hydrogen-fueled vehicles. And then that system would be provided and would be cooled effectively by water, which would be then used to supply hot water for heating or domestic hot water within buildings. And the question is would this be of value, and does this make sense? So what we came up with was we developed a model of a PEM electrolyzer process, and we gathered some data from a 1 megawatt system, and you can see that chemical process model and plus the data allows us to kind of work out, well, where could heat be captured from such a system and what might be possible. So the hydrogen gas itself was actually 63% efficient. That's where the 63% of the energy went to, but we've got 30 and 1.2% of the heat can be recovered from the stack, and then the hydrogen gas comes off the system hot. So there's two potential pathways for capturing additional energy from the process, which would normally be released. We then took that forward and established a scenario, which is what we called a 2030 hydrogen fueling station scenario, where that fueling station would be a 12 megawatt electrical connection, and it would run off peak. So between 1 and 6 a.m. The system would effectively fill itself up with hydrogen and produce just over a ton of hydrogen, which would be the equivalent for 15 trucks or 200 cars worth of hydrogen gas. And that itself, that process would produce 19 megawatt hours of heat per day. And the idea was that we would sell that heat itself back to the district heat network at their cost price. So consumers of this heat wouldn't pay any more than they would otherwise. And this works out to be about 190 homes worth of heat, or about 20% of what would be loosely termed a large heat network. So the observations from this analysis was that if you do it this way, obviously your price of hydrogen or heat is highly sensitive to the price of electricity, because it's the main cost to the system. And of course, we're planning to run the system off peak, but you know, the price of electricity obviously varies and varies for lots of different reasons. So yeah, this is one thing to be careful of. But overall, what we ended up with was a simple analysis, but there are other scenarios which ended up with much lower prices. And we also need to factor in that there's a need to displace this time. So this is 1 to 6 a.m. You would need to displace this heat so that it could be used in the rest of the day. So you would have to have an additional hot water storage for load shifting. So if you take your basic hydrogen producing system, and that's producing hydrogen for just the transport application, you ended up with a £2.50 per kilo cost price. But if you also sold the heat at cost price to the district heating network, the cost came down quite notably, taking off about a third of the price here. And then if you add in the heat storage model, which then suits all consumers from the transport to the end users of the heat, actually you end up with the most flexible solution with a minor increase of price. So what we're doing is we're continuing to look at this concept in more detail now, and we are pushing on with that. I think to kind of summarize the outputs, this co-production of heat and hydrogen for transport brings huge cost benefits to both local users of the hydrogen filling station, but also to the local community that sits around it. There's obviously scope that hydrogen can be used for industry or direct heating too, so it's not just about transport. What's fascinating, interesting, is that the electricity is distributed off peak, so rather than going through gas networks or trucks, you get a lower cost potentially as a result of that. And then we are putting forward this kind of more distributed model of hydrogen production for transport, and then integration into heat networks, which is a solution which decarbonizes both sectors. And this is obviously looks at this solution and obviously would bring an overall energy efficiency up from what is 63% to more than 90% when you add up what's possible here. And of course, it makes the whole system much more resilient too. So quickly, to just summarize, really, I've discussed some aspects of the decarbonisation of heat. I think I hopefully have illustrated that it's complex. It's certainly a challenge which cuts across every sector. It will cut across every industrial process. And I would imagine it will affect every person living in the UK over the next 30 years. There's hugely changing dynamics of price in renewable energies, and heat is likely to become more expensive, mainly because of a large capital expenditure is required to replace fossil sector. And some very difficult decisions need to be made, and there's still uncertainty actually as to what the best solution is for each region, sector and application. And I've given some examples of how heat can be decarbonised, and there's huge scope for innovation, way more than I've been able to talk about here. And there's an opportunity for solving this challenge. And I think that should probably be enough, because it's now nearly 8 minutes to 3 o'clock, and to say thank you very much for listening.
Okay, thanks very much, Andy. Excellent presentation, and we're going to have some question and answer session now. I think the first question was about this. If there was 10 times as much production, what proportion of heat of heat use would that be? So what's that equivalent of? How much can 10 times that increase in hydrogen allow us? And how does that compare with other fuel costs?
So the numbers that I put up, I guess at the beginning, which was talking about scaling up hydrogen production, those numbers have come from multiple sources. I guess predominantly they're from the International Energy Agency, and actually represented consumption globally. So they're talking about supply chain for, I mean, I'm talking about 10 times scale up, 100 times scale up, global production. So within those analysis, they would have done thumb in the air calculations about how much would they expect to be used by heat, how much would they expect to be used by transport, and how much would be expected to be used by industry or whatever. My view is that obviously all of those are fundamentally linked to the cost. Whenever you're seeing some of these analysis and you come back 2 years ago, 3 years ago, all estimates of how much hydrogen we would need were a fraction of what they are now. So people, as they're kind of more investing in the idea that hydrogen can go forward, are kind of revising up how much hydrogen we will need. So at the moment, I think a lot of the estimates are around using principally natural gas and reforming it and doing CCS. So the electrolyzer system is probably going to reach cost parity with that in the next kind of 15 years. I guess if you think about the numbers, current numbers is a third of the energy consumption is by heat, is for heat at the moment, and 20% is by electricity. You would need to build the equivalent of that electricity on again and on again for the renewable side in order to be able to deliver on the heat objectives.
So in your analysis, obviously going down the green hydrogen route, it's dominated by the cost of electricity. Did you factor in curtailment and the use of effectively excess wind, offshore wind, in that cost?
Yeah. So in the scenario when we looked at the combined hydrogen, the combined heat and hydrogen system, we played with some scenarios of actually some curtailment models, and it's very effective way of reducing the cost, because actually some of the cost becomes negative because you're not paying necessarily as much for your for the electricity itself, and that's obviously very effective in reducing the price. I think once you get to scale, the question really comes on is a negative electricity price or very low electricity viable? I think what I was really doing in the first half, which was to basically link the price of offshore wind. When offshore wind was available, it would be used to produce hydrogen directly. It wouldn't necessarily act as part of the standard kind of electricity market.
So actually, I missed a follow-on question from Helen, was about where does geothermal kind of fit into this?
So, well, geothermal is is probably something I didn't really discuss. Really, I didn't even touch on in the presentation. Obviously, geothermal is one aspect of one of the tools that you can throw at decarbonisation of heat. I guess it has its challenge with huge capital cost itself, but then you've got this potential long-term solution for the decarbonisation of heat that goes well beyond our lifetime. So there's obviously a huge opportunity there. I think in terms of lots of the projects going on, I think the key is to demonstrate that this can work, and it can work at scale. And if it can be done, then it makes excellent sense to do that. The challenge remains, is that realistically going to be as cheap as doing some of these other solutions? Because whilst natural gas has dominated the cost of heating, and if you take that away, what is the opportunity for everyone else? And that may well locally be geothermal, it may well be locally hydrogen, or it may well locally be electric, depending on what's already existing within the local infrastructure.
Okay. The question about, I guess, what came out of your comment about the insulation of housing and basically indicating that if we went for hydrogen boilers, then we wouldn't need to bother about insulating our buildings.
Well, it is interesting, isn't it? I mean, so there's a few fundamental things. I think, like historically, we've always been using fossil fuels, so there's always been a clear negative reason to use them. If we've made the solution net zero compatible, then that kind of reason not to do things and to waste energy, the dynamic changes in quite an interesting way. And I don't think we really thought that through. But yeah, in general terms, what the analysis shows is that basically the level of insulation that you need to do the retrofit to your house to be compatible with the heat pump is overwhelmingly large compared to just having hydrogen-based boiler system. That changes if you install the insulation at the moment of construction.
Yeah, so I think what you're alluding to is it's not just an efficiency thing. It's actually the temperature at which heat is delivered and the amount of heat that's delivered within a heat pump in comparison to what we've been used to.
Yeah, well, yeah, I think there's lots of I mean, like I said, it's very difficult to do the comparison, and the numbers add up best when you've got an existing property, it's already connected to the gas network, and it's a retrofit, and the way that you're used to using it as well is a factor as well. If you've got a new build, it maybe makes more sense to think about the heat pump model.
Yeah, I think another question, well, I guess a follow up that Matthew has said, but basically, that we shouldn't waste energy. But at the end of the day, it comes down to kind of, if we're going to transition to net zero, then it's got to be economically viable, and viable for everyone to be taken along with that. So
well, yeah, I mean, efficiency means lots of things,
yeah,
and it all depends on what you regard as having value. Like if you look at a photovoltaic system, it's got a 5% efficiency. No one really talks about the 95% losses in there, because it's energy that comes into the system which you wouldn't have captured otherwise. So a lot of it's about the perception of energy. If energy is freely available and it's low cost, then we should aim to be using it, right?
Yeah. Simone asked about, and I don't think you factored this in, but the factoring into your analysis, the health and environmental costs of fossil fuels.
I've not really, so I've done a comparison of Yeah, so the fossil fuel use, I guess by making the statement that it's got to be net zero, I've removed the need or use of fossil fuels and then compared the options. So I've effectively I've just ruled out all fossil fuels, I guess, in the analysis that I've presented. But the key bit is that when you look at the numbers, I guess the numbers from the analysis is that it's very difficult to beat the cost of fossil fuels without factoring in additional health and environmental costs, because the cost of in the analysis, the cost of hydrogen will always be higher than the cost of the natural gas.
So I think in terms of what you presented, there's obviously a need for government intervention. Do you know about government policies in this context to enable this transition towards hydrogen markets?
Well, I guess that the big thing is this hydrogen plan, which is due to come out later this year from central government. I have no idea what will be in this. I think the hydrogen happens, and it seems to makes most sense, like I showed, when it happens at scale. So it will need some kind of subsidy to go from where it is right now to the kind of scales that we need. We look at models like the electric vehicle market, which have been pulled up through a subsidy model and other grants to actually do the R&D, and this is a model which could work. Aggressive policies like banning internal combustion engines, gas boilers, these just accelerate the process because they show that something's got to replace the fossil-based option, and this, I think, is inevitable across this sector.
So again, a lot of the focus is on offshore wind to hydrogen. What do you think are the prospects of solar power to improving? Well, I guess the overall context of other renewables in the production of hydrogen.
So this is where it becomes about location. So there is potential for PV or some other solar-based technology to be used to produce hydrogen. It's cheaper than offshore wind in certain parts of the world. The question is it easy to get that hydrogen from there to here? And the answer is probably not. And we wouldn't necessarily be able to gain that value, especially when we've got offshore wind in its locality. There are people that are looking at doing PV to hydrogen to ammonia, and then huge transportation systems to move the ammonia. And I think there's a project in Australia which is doing that, which is interesting, and we keep an eye on it. We've looked at in another study looking at using PV to generate hydrogen in say Morocco, and then piping that hydrogen to the UK gas market. And again, it does look interesting and does look potentially viable to do something like that. Again, it's all cost driven, but doing it in a pipeline is cheaper than moving it around with a truck or other models.
Yeah. So I mean, we've talked a lot about fuel poverty, and we've got a situation where there is the potential to put 100% hydrogen to individual homes. A hydrogen boiler is roughly equivalent to the cost of an existing boiler, and we've got heat pumps that are, I guess, when you look at the total installation, it's something between 10 to 15K. What do you? I guess the question is about who bears the brunt of the cost for individual homes. What's your view on that and the link to fuel poverty or energy?
The first bit of, I mean, fuel poverty is not a new thing, and with a fossil-based infrastructure, costs were as low as they've ever been, I guess, for heating. The challenge now is that actually potentially more people will enter into fuel poverty as a result of moving to net zero, based on what the analysis that we show. So we need to address it. There's lots of factors involved there. And yes, it's quite seductive to think that actually, if there's an existing building, we retrofit with hydrogen, and that, I guess, aligns better with the kind of housing that already exists where there is fuel poverty than the heat pump model. But ultimately, it's a problem which has always existed, and I guess it just needs the right kind of economic model to actually address it and push the right people, push the problem onto the right people, so that it can be paid for and addressed directly. As a net zero problem, it just makes the whole thing a lot more difficult and a lot more complex, I think.
Mm. So there will be the need for some government intervention.
I'm not sure how we could do it otherwise.
Mm. Yeah. I was just wondering whether anybody else has any other quick questions they want to put in the chat, or even if you want to unmute yourself, you can put your question directly to Andy if you want. No. So I think we've come to a natural end to the webinar. So thanks very much again, Andy, and thanks for everyone joining the event. Don't forget that there's John Lewis is actually giving a presentation on the 9th of June at 12 till 1, and there's a whole program of other events. So we're really good to see you in the next event. Okay, thank you very much. Bye-bye.
Thank you for listening.